Everybody. Today we're going to look at worksheet 3.05, graphical analysis. I'm going to try to use both the graphing calculator and Google Sheets to demonstrate how to proceed with this curve fitting process. So let's take a look at data set 1. We're provided this information to plot a graph that is will be P versus V. In case you're unfamiliar with what these variables might represent, as it appears from the units, P stands for pressure in pascals and V stands for volume in cubic meters. So the question is, what is the relationship between pressure and volume? So what we need to do is we have to plot these points into a graph. And I think what we'll do first is we're going to use the graphing calculator. So I'm going to switch my screen. And so we'll take a look at using the graphing calculator. The first thing you're going to need to do is to go and click Stat, go over to Edit, and in columns L1 and L2, you're going to put together the data from data set 1. Once you have that data entered in, you're going to go to second y equals, which is the stat plot, and under option 1, we hit enter, and we want to make sure that the plot is on, that you have the scatter plot option selected, and that X list is L1 and Y list is L2. So I'm going to clear out of that. Before I hit graph, I'm going to hit zoom, and the best window is you can select by doing zoom 9, which is zoom stat. That zooms the window in strictly around your data that you've entered into the stat edit portion. So I'm going to hit option 9, and there I have my graph. So what we're going to do is sketch this out as it would appear on the worksheet. So let me just go back to my original share. Under dataset 1, we have a line to write our final expression, and we have two axes. So on the first set is going to be a sketch of the graph that we just got, along with the appropriate units. The second set of axes are reserved for the test plot. So I am going to switch now to my dot cam so we can write out formally what the graph would look like. So when you draw your axes, which are already provided, you're just going to want to label them correctly. So on the horizontal axis, we're going to want the volume in cubic meters, and on the vertical axis, we want the pressure in pascals. And without getting too technical, the points that were plotted there, if I were to connect the dots, would form a pattern that looks like that. So that's our first step, is to sketch the graph. Now what we want to do is attempt at defining the possible relationship between the variables. And so for that, I want to switch to this screen and look at my graphical methods summary sheet at all the possible relationships. And when I look and I try to compare what I have with what I know, the one that comes up for this relationship is this one right here. This is the hyperbola, which would suggest an inverse relationship. So we could also say it's a y proportional to 1 over x relationship. So that is the suggestion that I would make based on the shape of the graph. So I'm going to write that down. So we'll say that based on this, P is proportional to 1 over V. That's analogous to y is proportional to 1 over x. So what do I need to do in order to prove that that relationship is true? Well, as we've mentioned before, that any two quantities which are directly proportional to one another, when you plot them against each other, they should produce a straight line. So now we'll create our test plot. So our test plot will be generated by taking what's on the y-axis, we'll keep that the same, and what's on the x-axis we'll have as the inverse of v. So we need to create a new data set which takes our v values and finds their inverse. Now, whatever you do to the variable, you also have to do to the units. So the appropriate units for 1 over v would be 1 over meters cubed. You could, just as a side note, you could also write the inverse relationship with negative exponents. So I could have v to the minus 1 in units of meters to the minus 3. So that's another appropriate way if you prefer negative exponents rather than fractions. That is another possible option. And by creating this new graph, if the relationship that we have suggested is true, we should be able to produce a straight line. So let's go back into the calculator and produce this new set of information. So here, let me do this one more specifically. Here I'm going to go back to stat, edit, so hit enter, and I'm going to go over to the L3 column and highlight the very top cell where it says L3. That allows me to type in an equation here. And I can utilize the values that are in any column by selecting second and then a number from 1 to 6, which corresponds to the number of lists. So what I want to do is create a column which takes all the values in L1 and finds their inverse. So you could either do that by doing 1 divided by L1, or you could do L1 to the minus 1. Shouldn't make a difference. So let me do 1 divided by L1. So I'll type in 1 divided by, and you're going to see that it says L3 equals. That's what you want. And I'll do second 1, which gives me my L1. And when I hit enter, it will give me all the inverse values to these numbers here. If you made a mistake and you want to clear out that column, you go back up to L3 where the data set is included. You hit clear and then enter, and it clears that whole column out. So let me just show you that I could also do second L1 to the minus 1 and hit enter, and it finds those inverses for me again. So now I want to plot this new graph that would put my new 1 over v data on the x-axis, but I'm going to keep my y list the same. In order to change what you plot, you go back to second y equals. I'm going to go back into plot 1, and I'm going to change my x list from L1 to L3. So I'll hit second 3. So I'm keeping the y list the same, but that new data list that I created is now what's going to be plotted on the x-axis. I need to change my window because I'm using different numbers. So I'm going to go to zoom 9 again, and the hope is that if the relationship that we had suggested is true, then we should get a straight line, and that we in fact do. You can see that some of the points are really bunched together over here, but the majority that we can see do line up nicely along a straight line. So once you've proven that that relationship is true, then you can move forward with the final process of coming up with the equation of your curve. So let me go back to my camera, and let's write down, because we've now proven that that relationship is true. Let's write down what the equation would be. So having started with this relationship, knowing that it's true, we're going to bring these quantities down, and we're going to replace alpha with an equal sign and our constant of proportionality, and then we're going to have the possible intercept at the end. So in any of these examples, we're always going to be looking for the values of m and b. And for that, we're going to go back to the test plot, where the slope of the test plot is this value m that we're looking for, and the intercept here is the value b that we're looking for. We'll also have to address the units for these values, but let's first determine what those values are. So I'm going to go back to my calculator. To come up with a line of best fit, I'm going to go to Stat, go over to Calc, and option 4 is linreg. So I'm going to select 4. Now, the default, let me also mention that there are usually two different types of calculators floating out there. One where when you go to Stat, Calc, and select linreg, this screen will appear, which has these various prompts. If not, you might be just taken back to the main screen, and where you would see just this command here, linreg parentheses ax plus b. So the issue is that the default lists that the calculator uses to find the line of best fit are going to be L1 and L2. And so that is not the list that we are looking for. That is the original graph, but it's not the straightened version, the one that we linearized. So if I were to, let's say, follow through with L1, L2, you're going to see that I get information for A and B. Keep in mind that we're calling this letter M on our paper. That these numbers are not the numbers that we're looking for. The line that we generated stemmed out from the origin and went up positively. This suggests that there's an intercept of 14 and that the slope is 9, so that, or a negative 1.9. So the line would appear to go down given this equation. And what the calculator is doing is trying to come up with the line of best fit using the original hyperbola graph. So that's certainly not what we want. So what we need to do when we go here is change the lists. And the list to create the straight line is replacing L1 with L3. So I'll do second 3. If you do not have this option, then what you'll need to do when you get to the home screen and you see linreg ax plus b, you'll have to put in parentheses L2, comma, or L3, comma, L2. So that this has to be typed in next to linreg ax plus b in order for it to pull from these two data sets, this being my x list, this being my y list. So I don't have to do that because I'm prompted to use this option. So I'll hit calculate, and there are my numbers. My constant of proportionality is the value 4, and my intercept equals 0. So let me take us back to my paper where we can write this down. So the value for M is 4, and the value for B is 0. So to properly format this, we also need units for our values. I don't have to write the intercept because it's 0, so there's no point in including that. So we just have to worry about the units for our COP. So this comes from the slope of the test plot. And we think that slope is rise over run. and therefore we are going to take the units that are on our rise and divide it by the units that are on our run. So the units that are on our rise are PA, and the units that are on our run, if we select the first option, is 1 over cubic meters. Now, that's not a really proper way of leaving that, given that it's this complex fraction where you have a fraction within a fraction. So what we can do is we can reduce this complex denominator by multiplying the top and the bottom by the reciprocal of the denominator. So this divided by this is just 1, so we can do that without changing the problem. And that'll allow us to cancel out this whole denominator. And then what I'm doing is just multiplying across, which gives me the end result of a unit PA meter cubed. And so that's the unit for our constant. So the final equation becomes P equals our COP, which is the value 4, and it has units of PA meter cubed. And now I have the option to either say that times 1 or just write that and divide it by V. And so that is the equation for data set 1. That's the mathematical expression. Now, what's nice to be able to do is to see if all our efforts actually paid off and verify whether or not that equation actually satisfies our curve. So I'm going to go back to my calculator. First thing I'll do is switch back to the hyperbola data, which by going to second y equals, entering into the stat plot, switching the x list back to L1 and L2. Going to zoom 9 and confirming that I have my curve data again. I'll go to y equals and type in the equation, which I'm not going to use the letter V, I'll use the letter X, but essentially the equation is just 4 divided by X. And if I hit graph, you get the hyperbola, which goes through all of the points. So even though these are the values that were being measured from the experimental data, you now have a mathematical model which will predict the values of all possible points in between those that we find in our data set. So that is the end goal. We want to find our equation which satisfies the data, but in order to do that, we go through this process, but we have reached that goal, and so we are ready to move on to data set 2. So if we take a look at data set 2, here we have data that represents position and time. So I'm going to take this opportunity as a means to try out this whole curve fitting process using a combination of Google Sheets and Desmos. So I'm going to go to my Google Sheets page, and there I've already entered in. I've got a new spreadsheet. I've entered into the first column the T data, and in the second column the X data. That is the data I'm finding in data set 2. I've left the first row as the labels, and then I've included the values. So what I'll do now is highlight the 2 columns and go to Insert Chart. So you'll see that under Setup, there is Chart Type. I want to select the Scatter Plot option, which here they give you some suggested graphs, and so it's conveniently here for me to select. If you don't see that there, then you can scroll through and find the Scatter Plot option there. But In addition to that, I just want to point out that these boxes are checked. Use the first row as the header. So the first row is the header, and that means that it will automatically label everything for you from the title to the labels on the axes. And then this third box is checked as well. Use column A as labels. So that means that it's going to use the A column as your essentially your x-axis information. So we have our graph, and clearly I can make a note of the pattern. And so again, what we'll do is let's sketch this out and see what we can get. So on our graph, we're plotting t on the horizontal in seconds, and we're plotting x on the vertical in meters. And by sketching out the points, I can imagine connecting the dots, you get sort of a graph like that. So the question is, what is the possible relationship? I'll want to resort to looking at my summary sheet in order to get a better idea of what my options are. And looking at what's available, this curve looks like the most suitable choice to relate to this curve. So this suggests that y is proportional to the square of x. So I have to make sure to use what variables that I'm using in this example. And so the relationship that I would suggest is that x is proportional to t squared. So when the summary sheet says that y is proportional to x squared, it means that what's on this axis is proportional to what's on this axis squared. So even though we have the letter x here, we're not going to square x here because x is on a different axis. So just be careful that you don't make that mistake. So we'll want to create our test plot. And this relationship suggests that if I plot x versus t squared, that since these two quantities are directly proportional, that would produce a straight line. So I won't change my y list. It'll still be x versus x in meters, but my list on the horizontal axis will change from t to t squared. So that means that the units for t squared change as well. I go from seconds to now seconds squared. And the hope is that I can produce a straight line from that graph. So we're going to do that now in sheets. So let's go here. I'm going to need to create a new graph. And I'll do that by moving that out of the way. I'm going to go to a new column, create a new label. So I'll say t squared. I could use exponents, but rather than spend too much time on the formatting here, I'm going to just type it out this way. And then I'll go to the first cell where the values will be entered. And I'll type in equals first, and that way Sheets knows that we're going to actually do an equation here. I'll click this first cell in the first column, the 0.1, and you'll see you could manually type in A2, or you can just click that cell. And what we want to do with not only this value, but all the values, but we want to square them. So I'm going to use a little caret and hit 2 for squared, and I'll hit enter. So what I've done here is squared 0.1, that is 0.01. Now, you'll see this little box at the bottom right corner. If I hover over it, you get this little cross. I'll click and drag all the way down to the bottom of my data set, and I'll let go. And there you're going to find that the um, the values are all squared. So rather than spend time working to try to format the graph in a particular way, I find that the easiest thing for me to do, if I just want to be quick, is I'm going to copy my Y list and place it under the in a fourth column. So I haven't changed this list at all. I just want to have my X list, my new X list on the left, and my new Y list on the right, because that's what it will, it's easily recognizable to Sheets to graph your new graph correctly. So I'm highlighting these two columns now, the new X list and the copied Y list over on the right. I'm going to do insert chart. And as you can see, right off the bat, you get a straight line with t squared plotted on the horizontal and x still remains on the vertical. But the fact that we got a straight line proves that our relationship is true. And so we can go ahead and try to come up with the equation. And we'll do that by, let's go back to my page. Let's format this correctly. We start with this relationship. We're going to carry these quantities down, and we'll place alpha with an equal sign and our constant of proportionality, and we'll add to that our intercept. So remember that the COP and the intercept come from the slope and intercept of the test plot. This is the test plot. So that's a straightforward process in Sheets. What we'll do, go back to spreadsheet. So we'll select this graph, go over to the chart editor. Right now it's on set up with all those the scattered chart and these two checkboxes included like in the previous graph. But I'm going to go over to customize and find series, have that menu drop down, and go all the way to the bottom where you see these boxes. I'm going to click the trend line box and select it, and it gives us a nice line of best fit, which we can get the equation of by going to label. Where it says none right now, I'm going to say use equation. And so if I look at the equation of this parabola, or I should say the equation of the line of best fit for now, there are two numbers that were given. The slope is 3, and if you look at this number for the intercept, you might think, okay, 3.55, but if you miss this last part, e to the minus 15, that's scientific notation. That is representing 3.55 times 10 to the minus 15. So that's a decimal, and then 14 zeros before you get to the 355. So obviously that number is so close to 0 that I am just going to ignore it and drop it. And we're just going to make use of the slope as being 3. So let's write it out. The M value is 3, and the B value, it was a number close to 0. So we are going to drop it. So the equation becomes x equals 3, make some room for units, times t squared. The intercept is close enough to 0 that I will ignore it. What are the units for my COP? The units come from the test plot. I do rise over run. And so with what I have in parentheses here, and some people are still making the mistake that the variables I use as my dependent variable are these letters here. And then what I have in parentheses are the units. They get tied to the values. So I will use the units meters divided by seconds squared as my unit for the COP. And so this is the mathematical expression for data set 2. Now, just like the last example, there's some satisfaction in seeing our work and proving it that it is in fact the equation for our curve. The only issue is that in order to try to get plot an equation that could go through these points for you, might require that you create a new data set and type in the equation into a particular cell, and then have it perform a calculation to produce an expanded set of data. But I'm not going to go through that trouble. One concern you might have, though, is let's say you had a graph like this and you wanted to include it in your future lab report. I would like to see a best fit trend go through here. And you can do that without relying on a particular equation. If I have this graph selected, I go to trend line. You obviously don't want a line of best fit, we want a curve. You can go to linear, where you have type, and you could change the chart type to something else. So a polynomial should be a good fit for that. It's a polynomial of degree 2 because it's a t squared. So that should be an appropriate trend to do. So let's so this doesn't, I want to actually see the equation that we just constructed here. So what I'm going to do now is to go to Desmos, and in Desmos, for my own satisfaction here, I've taken the data from data set 2 and I've plotted them here. You can plot a set of data by going to the plus sign, and by the way, desmos.com/calculator, and off to the left here, go to the plus sign. You can add a table and you can type in your values. You have to make sure that the circle is selected so that you can see your points. My data range is very poor, so I'm going to go to the little wrench here, graph settings, and I'm going to change the scale. So on the X list, I want to go, I can really start at 0 and go all the way to 5. And in the Y list, I can also start at 0 and go all the way up to 75. And if I want, I could just zoom out just so I can see all the points like so. Now in the next area, I'll type in the equation. The equation's basically x equals 3t squared, but here we're going to just say y equals 3x squared. So I'll just type in 3 times x squared. And there we see the parabola, and it goes through all of our points very nicely. So that gives you that satisfaction to see the graph going, the equation producing a graph that goes through those points. Let's move on to data set 3. All right, data set 3, we have A in months, W in pounds. So this is likely some kind of weight, and we're looking at how the weight of something changes over the series of months. Could be a newborn baby that maybe started out in its first month with weighing 7.3 pounds, and after 1 month, that baby began to weigh 9.4 pounds, and so on. So I'll use sheets again to model this data set. So I've also included that here, and I will go through the process a little bit quicker this time. Highlight, insert, chart, and I have a data set. Now, if I'm looking at what this could be, I'm already at 0, 0. So although these points don't seem to be on the straightest of lines, I feel fairly confident saying that the points that I have here are in fact points that are on a straight line within some margin of error. And here again, we're plotting how much the weight is changing over time. Let's just say I actually think that we can go a little bit further to the left. So I'm going to go to customize the horizontal axis, and where you see min and max value, you can change the window. I'm going to make sure that 0 is selected. Yeah, there we go. So I can see a straight line extending all the way out here. Now, you might think it's the one of the curves. So if we look at what other curves we either have the straight line, the diagonal line, or we might have this over curve. So if you want to take the easy way out, you could just come up with the line of best fit for this data set. And that we would do by going up to series, checking the trend line box, and inserting the label where we would have these set of numbers. And within some margin, there's some points that are below the line and some points above the line. Now, the only other possibility that I would have suggested would have been the over curve. But let's see if that actually gives us anything significant. If it was the over curve, that's the y squared proportional to x. So that would take what's in my second column, W, and it would square it, which would mean pounds squared. And I would type in equals this squared, and I would extend that out. So what I'm going to plot now is just, continues to be my X list, and this is my new Y list. Now let's check out the chart. And it actually is pretty linear as well. So let's see, we'll customize, go to horizontal axis, type in 0. And let's add in a trend line. It doesn't completely straighten it out by doing that, but it's not a terrible fit. It's a matter of what model might better suit the data, because we're limited in exactly how much data we have. But if this trend were to continue, is it more exponential or is it a linear trend? And so that you could argue that it's probably more likely to be a linear trend than anything else. So I'm going to stick with the linear trend for this and go ahead and tell you guys what the equation would be. So let me switch my screen to my camera, and we will write that. Let's see. We're going to write here that W was proportional to A. So W equals MA plus B, where A was approximately 1.3, B was approximately 6.6. The equation gave us this line, which had W in pounds on the vertical, A in months on the horizontal. So the equation becomes W equals 1.3. The units would be from rise over run, so it would be pounds per month. Our variable A, plus the intercept, which is 6.6, and the intercept always shares the same units as what's on the vertical axis, so that's pounds. So this would suggest that when A is 0, that W is 6.6. So it could mean that if we're talking about a child, that the child weighed 6.6 pounds at the time it was born, at 0 months, and that it's increasing its weight by 1.3 pounds every month in a linear fashion. So if that data set works for how the baby is growing, then that's an appropriate trend to use. We will now look at our last of the 4 data sets, which is going to involve T in seconds, V in meters per second. So let's go to and use the graphing calculator for this one. So I'll go to Stat, Edit, and there I have my data set 4, the X list in L1, Y list in L2. Let's make an observation as to what the graph looks like. I'll go to second Y equals. I want to go into plot 1. I want to make sure that it's on, scatter plot, L1, L2. Make sure I clear out what I had in the Y equals. Clear out of that, go to zoom 9, and that should take me straight to the graph. So clearly I see this as the an example of the over curve. So if we go back to our possible relationships, this would be an example of the over curve, which would square the y and have that be proportional to x. So we're going to try that out. So let's format some of this. The graph we would label here with T on the horizontal in seconds, V on the vertical in meters per second. And what we get is the parabola that's an overcurve. That would suggest that V squared was proportional to T. So to create our test plot, we would want to plot, in order to get a straight line, T as it was on the x-axis, but we would take V and we would square it on the y-axis. And what we do to the variable, we also do to its units. So if I had meters over seconds, then I want to square the meters over seconds. So quick note about that. If I square meters per second like this, the square distributes to both the top and the bottom. So your best bet is to write out the units like this, because otherwise you might mistake when you're saying this. If you're speaking about these units, you might say meters per second squared, but you would also say this meters per second squared the same way, but this is not the same as this. This is correct. So I would either say meters per second the quantity squared, the whole thing squared, or meters squared per second squared. So we want to prove that that relationship is true by going back to the calculator. And unlike the last example, by the way, which didn't seem perfectly linear, it certainly didn't have this as clear of an over curve trend as this one did. So, you know, I think we went with our best possible option in the last example with the linear trend. But let's go to Stat, Edit, and create our new column. What we want to do is square V. These are my V values. So I want to take what's in L2, second L2, and I want to square it. When I hit enter, it squares all the numbers. In order to create the new graph, I go to second Y equals, and under plot 1, I want to change what's on my Y list from L2 to L3. So I'm going to hit second 3. So now I have options. X list is L1, Y list is L3. So I'll do second quit to get me back to this screen. I'll go to zoom and click 9, and the hope is that we get a straight line. And that is a very nice straight line. So that proves that our relationship is true. We can go ahead and find the line of best fit by going to Stat Calc, option 4 linreg, and I want to have my X list as L1 and my Y list as L3. That's where my V squared data is. I'll hit enter, calculate, and here I get my COP is 333.3 repeating and no intercept. So let's format that on my sheet. So first of all, starting with this relationship, we bring our quantities down. The equation will start with V squared equals, we have our COP and our intercept, though the intercept is equal to 0, so we really don't need that piece. And what we have for our COP is 333.3 repeating. And we would now want to ask what the units are for the COP. Well, it's going to come from the test plot, and it's going to be rise over run. What's on the rise is meters squared over seconds squared. And then we divide by what's on the run, which is seconds. Now, just to be sure that you know how to simplify this properly, we go through the same process that we did before for simplifying a complex fraction. We multiply top and bottom by the reciprocal of the denominator. So that allows for what we have down here to go away. And what we see that we're going to be left with here, multiplying across, m squared times 1 is m squared. S squared times s is s cubed. So the units that we're left with here are meters squared over seconds cubed. And so that's what I'm going to put here, meters squared over seconds cubed. And so this becomes the final equation. Remember, we don't need the intercept. But if I want to check to see that that equation actually goes through all of my points, you have to solve this for v. And so what I do is I square root both sides. And so under the square root, I have 333.3. Repeating, units are meters squared over seconds cubed times t. So let's see if this equation works. We're going to do that by going back to our calculator, switching the graph back to the original plot by switching back the y list from L3 to L2 and choosing the appropriate window once again. And I'm going to go now in y equals and hit second x squared, which is the square root. And I'm going to type in 333.3, and that's rounding it, but I think that's good enough, times x. And that should give me the graph that I'm looking for. And there it is. Even with rounding, we are able to get a graph that appropriately goes through all of our points. The challenge problems I will do separately, but these are the first 4 problems that you are responsible for. See you guys.